Okay, this is part 2 of the lecture on capacitance. We use capacitance to introduce students to the two basic types of circuits, what are referred to as parallel and series circuits. Okay, let me describe to you what is meant by a parallel circuit. First, essentially you have multiple loops to a single circuit. So let's say it right here is a battery, like so, which has a voltage V associated with it. We have the positive side and the negative side. And then I hook up to it right here a single capacitor, first of all, with capacitance we'll say C1. And then right over here, another loop, like so. We have a second capacitor here, like so. Let's say that this capacitor here has a capacitance C2 associated with it. Once again, the capacitances of these capacitors depends upon their area and the plate separation from part 1 of the lecture. Okay, so we hook this up and then turn it on, and what happens? Well, the two capacitors charge up, and then they will finish charging when we have two pieces of metal here that are equipotential surfaces. Right here is a single piece of metal, like so. Right here is a single piece of metal. So electrons will stop flowing to and from the capacitors when each piece of metal is an equipotential surface. So then therefore there is no potential difference between here and here for this top piece of metal. There is no potential difference between here and here, like so, because this entire piece of metal here is an equipotential surface. Same thing down below. This piece of metal right here is an equipotential surface. So there's no potential difference between here and here. There's no potential difference between here and here. Therefore, the voltage of the battery, the potential difference between here and here, is the same as the potential difference between here and here on this capacitor and here on this capacitor, like so. What we're interested in calculating here is what is referred to as the equivalent capacitance. Basically, this entire circuit behaves mathematically as if this is just one capacitor. And we want to calculate then, therefore, what is referred to as the equivalent capacitance. Okay, before I show you how that's done, pause this lecture and then take a look at the short demonstration video that I have uploaded for you called Capacitors in Parallel. Make sure that you take a look at that. Okay, now that you've done so, let me lead you through a calculation here of how we find what is called equivalent capacitance. Okay, this capacitor here, once it's charged up, it has a charge Q1 associated with it, positive and negative. This capacitor over here, once it's charged up, has a capacitance, or excuse me, a charge Q2 and a negative Q2 associated with it. The total amount of charge, however, that's present in the circuit is the sum of the two. Like so. And now remember that charge is equal to capacitance times voltage. The voltage, however, is the same for that of the battery and across each capacitor. So then therefore on the left-hand side, the total amount of charge that's present in the circuit is equal to, first of all, what we're trying to find, called C equivalent, the equivalent capacitance, multiplied by the voltage V. And then we have Q1 and Q2. Q1, the charge on capacitor number 1, is equal to its capacitance C1, and then multiplied by the voltage V. And then over here, charge Q2, well, that's going to equal to that capacitance C2, but then multiplied by the same voltage V. The voltage V cancels out from the expression. So the equivalent capacitance is then therefore equal to C1 plus C2. So when you hook up capacitors in parallel, the equivalent capacitance, it all behaves as a single capacitor, is just equal to the sum of the capacitances. Okay, take a look at your smartphone. When you press your smartphone in various ways, you are basically pressing down on capacitors that are in parallel. An ordinary keyboard for your laptop, for example, all of the keys on the keyboard are all capacitors that are hooked up in parallel. When you press down on one of the keys, by the way, you are discharging a capacitor. When you press on your smartphone, you are discharging a capacitor. So when you have capacitors hooked up in parallel, you are then therefore storing more energy, the capacitance has increased, and then therefore it requires more energy to operate, okay? Okay, and then the second basic type of circuit is what is referred to as a series circuit. Okay, in a series circuit, you have one circuit element, as we say, one after another in a single loop. So let's say, for example, once again, right here is a battery, high and low potential and voltage V. And then right here is a capacitor we'll call C1. And then right here is a second capacitor that we'll call C2. There are three pieces of metal here on this diagram. Right here is one. Right here is 2, and right here is 3. When electrons flow to the negative side of the capacitor and from the positive side of the capacitor, the charge on each capacitor is the same. There's a positive Q here, for example, and a minus Q down here, like, for example, in my original diagram that I described in part 1 of this lecture when charging up a single capacitor. What happens to this piece of metal right here? This piece of metal is uncharged to begin with. Therefore, it becomes polarized when charge gathers here and here on these sides of these respective capacitors. This side of the piece of metal becomes negatively charged. This side of the piece of metal becomes positively charged. Notice that the negative charge is being attracted to this positive charge up here. Notice that this positive charge is being attracted to this negative charge right here. It's important to understand, however, that this single piece of metal right here is uncharged to begin with, and it then becomes polarized. One side of it is negative, and the other side of it is positive. Okay, now how do I arrive at a statement for equivalent capacitance with a series circuit? Well, we note first of all the following. The potential difference of the battery here is V. That's the same thing as the potential difference between this point here and this point here, because once these capacitors have been charged up, this right here is an equipotential surface, and this right here is an equipotential surface. So then therefore, if the potential difference between those two is V here on the diagram, it's also the same thing here. Therefore, the potential difference across this capacitor, call it V1, plus the potential difference across this capacitor, call it V2, that then equals the total amount of V. Just think of it as like climbing a hill or different heights adding together to give you a total height. So let's say that this total height, if you will, right here is say 10 feet, and this height here is 5 feet, and this height here is 5 feet. 5 feet plus 5 feet equals 10 feet. That's the easiest way of thinking of this, once again, in terms of differences in height, differences in electric potential. All right, so the total voltage V of the battery is V1 plus V2. And now on the left-hand side of the expression, voltage is charge over capacitance. In this case, C equivalent, which is what we're interested in calculating. On the right-hand side, I'm going to replace those V's there with, once again, Q over C, but the Q's are the same as is being indicated here in this diagram. So Q over C1 for voltage V1, plus then Q over C2 for voltage V2. All of the Q's now cancel out, like so. And then therefore we end up with this expression here to describe equivalent capacitance when capacitors are placed in series. When capacitors are placed in series, the overall capacitance C equivalent therefore becomes less and less as you go. So ultimately you store less and less electric potential energy by doing this, but there are certain advantages for doing a circuit like this, as you'll discover a little bit later on when we get deeper into circuits after spring break. Okay, now make sure that you watch the demonstration video that I've posted for you called Capacitors in Series. It then illustrates how the voltages add together to give you the total voltage V. There are two lecture examples here for us to cover in part 2 of today's lecture. At this point, go ahead and copy down into your notes the first of those two examples. I have it up here on my screen. I'm going to erase the board and then I'll refer to that. Okay, the first of the two examples that we'll look at here is an equivalent capacitance problem. There's a diagram associated with this problem. I didn't draw it for you on the lecture examples notes. However, let me go ahead and draw it here on the board. Okay, the circuit element that we're trying to find the equivalent capacitance of looks like this. Like so. So we have a complicated circuit diagram here of some sort like so, and then we have capacitors here that all have the following value of capacitance. C, like so, where each one of these is equal to 1 microfarad. The symbol mu here means micro. It means 1 times 10 to the minus 6. Okay, then over here on the left-hand side are just other things in the circuit that we're not concerned with. What we're trying to find here is the equivalent capacitance here of this circuit element. What we do basically is we work from the inside out. You start small and then work your way outwards on the diagram. So what I'm going to do right here is find the equivalent capacitance, first of all, of these two guys here, which are in parallel with respect to each other. I'm going to call this C equivalent 1. So C equivalent 1 for capacitors in parallel is just the sum of the two. It's C plus C. This is equal to 2 microfarads. Now what I'm going to do is erase this portion of the diagram and replace it with a single capacitor which has capacitance C equivalent 1. You'll probably want to pause and just redraw the diagram. Like so. So right here is now C equivalent 1. So now what do I do? Well, C equivalent 1 right here is in parallel with this capacitor over here. So these guys here behave as a single capacitor. I'll refer to that as C equivalent 2. So C equivalent 2 is going to be the sum of these two because, once again, these guys here are in parallel with respect to each other. So C equivalent 1 plus this C over here. So this is 2 microfarads plus 1 for 3 microfarads. Like so. So these guys right here behave as a single capacitor with equivalent capacitance, C equivalent 2. I'm just going to erase this portion of the diagram and redraw it. I suggest you do the same. You pause the film, of course, if you have to. Okay, so right here now is the C equivalent 2 that we just found, and notice that it's in series with this last capacitor here. So then therefore I use the series relationship to now find the equivalent capacitance of the whole thing that we're trying to do. So I'm just going to call that now C equivalent, like so. So it's the 1 over relationship for capacitors in series. So 1 over C equivalent 2 plus 1 over C for this capacitor here. So this is 1/3 plus 1 over 1. That's a total of 4/3. However, take the reciprocal now, which is 3/4, to find the equivalent capacitance of this entire circuit. So C equivalent, therefore, is equal to 3/4 microfarads. Like so, when you do the math. Okay? Okay, obviously there is all sorts of computer code that is written for all of this when it comes to doing detailed circuit analysis, but this, of course, covers the basics. Okay, next, go ahead and copy down the second problem from the lecture examples. There's a diagram associated with that as well. I'll go ahead and copy it on the board for us in just a moment. Okay, let me do some erasing. Okay, so for the second problem, we have the following diagram associated with it. Okay, in this case, we have a battery with a voltage V0, we're referring to it as. Okay, and then I have the following circuit elements. like so. This is capacitor 1, capacitor 2, and capacitor 3. And then I'm keeping the numbers here very easy for us to work with in the example. Okay, so the voltage, first of all, of the battery, V0, that's given to us as 10 volts. And then I have the three capacitances. C1 is 1 microfarad, and we can just write it as micro here. We don't have to write it as 10 to the minus 6. And then C2, 2 microfarads, C3, 3 microfarads. It says, find the voltage and charge across each capacitor given this information. Okay, so we charge this up, and then what happens? Well, over here on the left-hand side of the diagram, because these guys here are in series with respect to each other, they are then therefore going to have different voltages. This right here is going to be a voltage V1. This right here is going to be a voltage V2. What is the sum of V1 plus V2? Well, it's the same thing as the potential difference of the entire circuit, V0. How many pieces of metal are here in this diagram? There's actually only 3. One is right here, the second one is right here, and then the third one is right here. So then therefore, once everything has been charged up, this potential difference here of V0 is the same as this potential difference here is the same as this potential difference here. So V1 plus V2 is equal to V0. So. Okay, now what about the potential difference here across capacitor number 3? Well, the potential difference here is the same as the potential difference here is the same as the potential difference here. So then therefore the potential difference here across capacitor number 3 is V0. This then means that immediately we can now calculate the charge across that capacitor. Let's call that charge Q3. So right here is the positive side, positive Q3. Here's the negative side like so. And now that Q3 is equal to capacitance number 3 multiplied by the potential difference across that capacitor, which is V0. So this is 3 microfarads multiplied by 10 volts. This is then therefore 30 microcoulombs. Like so. Okay, now what about these guys over here on the left-hand side? They're in series. So then therefore they have the same amount of charge on each capacitor. Let's, however, call this one here Q1, positive and negative. Let's call this one here Q2, positive and negative. But because these guys here are in series, those capacitors that is, we know that Q1 is equal to Q2. Okay, now let's go ahead and take this expression here and plug into it the following. Voltage number 1 across this capacitor. This is going to be the charge Q1 divided by the capacitance C1. Okay, this right here, voltage number 2, is going to be the charge, we're calling it Q2, divided by capacitance C2. Like so. And now I have right here 1, 2. 2 equations and 2 unknowns, Q1 and Q2, which I can now solve for. Once I have those charges, then the last thing that we can do is find the voltages V1 and V2, as the problem asks us to do. Oh, so at this point, we just have to do a little bit of algebra. Let's go over here and let's replace the Q1 here with just Q2. Like so, and now let's go ahead and solve for Q2. So to do so, I'm going to factor out a Q2 here from each term. Like so, and then divide by the parentheses here now to get Q2 by itself. When I do, keep in mind that this is the same thing, however, as Q1. So let's just go ahead and calculate it. Like so. And then when I do make this calculation, it's going to be in terms of microcoulombs. So in the numerator, I have here 10 volts. And then divided by 1 over 1 plus 1 over 2. So 1 plus a half is 3 halves, so divided by 1.5. And this then gives me a value here of about 6.67 microcoulombs. Now that I know what that charge is, Q1 and Q2, we can then complete the problem by finding V1 and V2. So if you take a look at capacitor number 1, first of all, Q1 is equal to capacitance number 1 multiplied by voltage V1. So now I can go ahead and find the voltage V1 by doing this. So then therefore this is 6.67 microcoulombs divided by 1 microfarad. This then ends up being 6.67 volts. Like so. And then lastly here, voltage number 2. That's going to equal the total voltage V0 and then minus V1. So 10 minus then 6.67 is 3.33 volts, like so. Okay, that's as complicated as we'll get here with respect to basic circuit analysis involving capacitors in series and parallel. So this will then conclude part 2 of today's lecture. This is basically the final lesson prior to spring break. Make sure that you take a look at all the due dates associated with the CK12 work and also the last problem set. At this point, you can do the last problem set. Ultimately, all the assignments prior to spring break are due by Thursday at 3 p.m. Make sure that you look at all the due dates and times that those assignments are due as we go through the remainder of this week and then ultimately move into spring break. I wish everybody a restful spring break. Make sure that you stay safe. Social distancing is saving lives. Today's shirt is Amon Amarth. Take care.